Have you ever wondered what it really takes to go from writing .NET code that just works to building APIs that are truly professional, the kind that are ready for production? Well, today we're going to open up the Architect's Toolkit and find out exactly that. So what is it? What's that line that separates code that's just good enough from software that's robust, scalable, and easy to maintain down the road? That's the big question we're tackling today, and every single concept we cover is a new tool to help you make that leap. All right, here's our game plan. First, we're going to lay the foundation with the solid principles, the blueprint. Then we'll look at the actual machinery of an API, how it handles requests. After that, we'll dive into managing all its different parts and settings. And finally, we'll add some pro-level patterns to really make it shine. Think of it like we're building a high-performance engine, piece by piece. Every great building starts with a solid blueprint. And for software, that's what the solid principles are. And trust me, these are not just some academic ideas you learn and forget. They are the absolute fundamental rules for writing clean, resilient code that can actually stand the test of time. First up in our toolkit is S for the single responsibility principle. The idea is simple. A class should only have one reason to change. Now, just look at the problem on the left. This one class is doing everything. And the real danger? A tiny, innocent change to how a report looks could accidentally break how payroll gets calculated. No way. By separating these jobs, like we see on the right, you can update one part with confidence, knowing you haven't just torpedoed the whole system. It's all about minimizing risk. Next up, O for the open/closed principle. Now, this one is really powerful. You should be able to add new features without changing existing battle-tested code. Think about it. If you have to crack open your main area calculator every time you want to add a new shape, you're just asking to introduce new bugs into code that was working perfectly fine. The solution? You abstract it. Create a base shape class, and now you can add all the new shapes you want without ever touching that core calculator logic again. L stands for Liskov substitution. Yeah, it sounds a little intimidating, but the idea is actually super simple. It just means that a subclass has to be a true substitute for its parent. If your code expects a bird and you give it an ostrich, calling the fly method shouldn't crash your entire program. If it does, your abstraction is wrong. An ostrich isn't really a substitute for a bird if you're talking about flying, right? This principle forces you to be more honest and create predictable code. And now for I. Interface segregation. The takeaway here is don't force a class to take on methods it doesn't need. That giant I worker interface is a classic code smell. A robot worker, it works, but it definitely doesn't eat, so why force it to have an eat method? The answer is to break up that big, bloated interface into smaller, more focused ones, like iWorkable and iFeedable. That way, your classes aren't carrying around useless baggage, which keeps your code lean and clean. And finally, the D for dependency inversion. Your high-level logic should not be welded directly to the low-level details. A switch class shouldn't have to know or care if it's controlling a light bulb or a fan or a coffee maker. By making both the high-level switch and the low-level light bulb depend on an abstraction, like an iDevice interface, you totally decouple them. This makes your system incredibly flexible and, maybe even more importantly, way, way easier to test. Okay, so Solid gives us the blueprint for building really well-designed parts. But how do all those parts actually work together when a request hits our API? For that, we need to understand the machinery of the request pipeline.
This whole pipeline is built from these little pieces of code called middleware. And honestly, the best way to think about them is like a series of checkpoints on an assembly line. Each piece of middleware gets to inspect or even change the request before passing it along to the next one. This is how we handle all those crucial things like authentication, logging, and error handling.
And this slide shows that flow perfectly. So let's follow a request on its journey. It comes in at step 1. First, it might hit the CORS middleware to check if the request's origin is even allowed. Then it passes through our exception handler, which is like a safety net. After that, authentication checks if the user is who they say they are. And only then does it finally reach your actual business logic in the API controller. Then the response flows back out through those exact same layers, but in reverse. And that is why the order is so critical.
All right, next up in our toolkit, how do we manage all the connections and settings for the different parts of our app? This is all about building code that's flexible and configurable, not brittle and hard-coded. And the star of the show here is Dependency Injection, or DI. The great news is it's built right into ASP.NET Core. See, instead of a class creating its own dependencies, like making a new database connection itself, we inject it from the outside. Hey, remember that dependency inversion principle we just talked about? Well, this is how you actually do it in the real world. It is the key to building testable, loosely coupled systems.
Now, when we set up these dependencies, we have to choose a lifetime, and picking the right one is absolutely crucial. Transient gives you a brand new one every single time it's requested. It's perfect for lightweight, stateless things. Then you have scoped. This is the real workhorse for web APIs. It gives you one instance per HTTP request, which is perfect for things like a database context. And finally, singleton. This gives you the exact same instance for the entire life of the application. You got to be careful with this one, but it's great for things like a global caching service.
So what about our configuration settings, like API keys or connection strings? For that, we use the options pattern. Instead of grabbing raw strings out of a config file, which is just asking for typos, we bind a whole section of our JSON settings to a strongly typed C# class. No more magic strings. But here's where it gets really interesting. Not all of these options interfaces are the same. And as this quote from developer Mukesh Morgan shows, picking the wrong one can cause real-world headaches. A feature flag wasn't working in production because the configuration wasn't reloading. The fix itself was tiny, but the debugging, that was painful. So this table right here is the key takeaway. IOptions reads the config once, when your app starts up, and that's it. It's perfect for settings that never change. IOptionsSnapshot will reload for each new request. But IOptionsMonitor, that one can reload in real time and even tell your code when something is changed. So here's my advice. Just default to IOptions. Only reach for IOptionsMonitor when you know you need that dynamic reloading, like for those super important feature flags. We've got our foundation, we've got our machinery all configured, now it's time for the professional finishing touches. These are the patterns that take an API from just being a side project to being a real product. First off, API versioning. Your API will change. It's a living thing. And you can't just go changing endpoints and breaking things for all your existing clients. Versioning, having a /v1/products and then a /v2/products, lets you introduce those big changes while giving everyone else a clear path and plenty of time to adapt. As you can see on the timeline, it's about professional evolution, not just chaos. Next, let's talk about cores. By default, browsers have a security rule. A web page at, say, mycoolsite.com is not allowed to make API calls to yourapi.com. Cross-origin resource sharing is the mechanism you set up on your API server to explicitly say, hey, it's okay, I trust requests coming from mycoolsite.com. If you don't get this right, your front-end apps just plain won't work. And this one's a big one. Please, do not litter your code with try-catch blocks in every single one of your controller methods. It's just messy, and it becomes a nightmare to maintain. A much cleaner, much more robust way to do it is with a global exception handling middleware. It's like the ultimate safety net, catching any unhandled errors from anywhere in your app, logging them consistently, and sending back a nice, clean error response to the client. And there we have it. We've just assembled a really powerful set of tools, taking us all the way from the basic blueprints right up to production-ready patterns. So let's do a quick recap of what's in our toolkit now. The solid principles, that's your architectural blueprint. The middleware pipeline, that's the core engine. Dependency injection is the power tool that connects everything. The options pattern handles all your settings safely. Versioning and cores make your API professional and secure. And of course, global error handling is your ultimate safety net. You now have the architectural mindset and the practical tools to build not just good, but really great production-ready .NET applications. Your toolkit is packed, so the only question left is, what are you going to build with it?